Welcome back. We're continuing our talk on two-sample hypothesis testing for Z and T, and in this video we're going to branch out into the confidence intervals and variance. So in the previous video we introduced the concept of independent two-samples testing. We're going to extend that here, and in the future video we're going to go into paired two-samples and other aspects. So let's go ahead and get started first with T confidence intervals. Now the T confidence interval, we work with it just like any other confidence interval, and the idea is that it is some range of estimates that contains a population parameter at a given level of confidence. Keep in mind, any confidence interval that could contain a value of 0 are not statistically significant, meaning that it is potentially that there's no difference in the means of what you're looking at. When we're constructing this means interval, it is similar to the confidence intervals of previous areas, and we're having some mean difference. This is group 1 minus group 2, so the difference in means multiplied by the t critical value, plus or minus, and then we have the standard error there, which was the square root of the variance of group 1 divided by the n of group 1, plus the variance of group 2 divided by n of group 2. If we want to go ahead and use an example here, we could ask, do men and women differ by their self-perceived level of socioeconomic index? Let's consider a 95% confidence interval. So I'm going to take this same confidence interval and build it in. And I'm going to use the GSS, the General Social Survey data, 2016 specifically. And just getting some summary statistics here, I'm going to use an aggregate function in R, and the variable for socioeconomic index is SEI10. I called it SEI10.fix because I had to take the variables and make sure I put them into numerical values so they appropriately match what they're supposed to be. And then we're going to separate this by gender, looking in the GSS data set and the mean. And it tells me that on average, men have an SEI of about 47.8 and women have an SEI of about 45.3, which gives us a mean difference between men and women of 2.45 rounded, with men being the higher. Let's go ahead and put this into a t-test to see how we can go ahead and go from here. Now we need, no, I'm sorry, not a t-test, confidence interval. And in order to move with this, we need to find the t critical value. But how many degrees of freedom do we have? Well, I'm going to go ahead and use functions in R to help tell me our sample size. On the screen here, I'm showing you the Desker function inside Summary Tools on the GSS SEI10 fixed variable, and I'm filtering it to only show me men. And I have an n valid of 1,234, and I do similarly for women, and I get 1,512. Following the independent sample's degrees of freedom, I add those two values together and subtract 2, so my degrees of freedom are 2,744. Now that's huge. If I try to look that up on most t-tables, it's not going to go that high. But what I could do is just take the next highest value and use that as an estimate. And usually, if the estimates are higher than what they need to be, you're just being more conservative in your results. Now, if I want to find this out in R, I can also use it to help to generate the t critical values at given degrees of freedom. And so I can use a QT function and look at the lower tail with a probability of 0.025, comma my degrees of freedom, 2,744, and it says I get a t lower value of negative 1.96 rounded, and similarly I get the upper tail at positive 1.96 rounded. That 1.96 may seem very familiar. That is the z-score critical value. This isn't 1.96 exactly, we've got the long decimal chain on it as well, but it follows in line that the t's curve is approximating z at this point because our sample size is so large that they become so similar to each other. But just to kind of show you as I'm looking up here, I could go ahead and look this up on a t table, and the lowest row I have here stops at 1,000, and after that it just says z. And so we can see that with degrees of freedom of 1,000 in our column for alpha, we have a t critical value of 1.962, and anything higher than that really starts to approximate z at 1.96. So let's go ahead and continue to construct our confidence interval by gender. We know that the mean difference is 2.45. Our t critical value is 1.96, plus or minus, and what I didn't show the calculations for was getting the standard deviation, which I plugged into the formula here, that men have a standard deviation of 22 and women of 23. Those are getting squared because we're working with variance here. Divided each respectively by their n's, sum the difference, plug it into square root, work it out, and we get a confidence interval of 2.45 plus or minus 1.96 points. Now, this confidence interval is not the interval of the SEI itself. It's the interval of the difference, and that's why we were concerned to see if that difference of 0 could appear in here. And the confidence interval of the difference in SEI is somewhere between 0.77 and 4.14. So we could say that if we were to iterate our samples over and over and over again, that 95% of the time our interval is going to contain the population difference of these two particular means. And in this particular sample, we believe it would be between 0.77 and 4.14. Now, I want to see that a t-test will also give us our reference results. So I can bring up a t-test, and we're going to plug in the SEI variable, tilde the gender variable, and tell it that we're looking in the GSS. And that's going to spit out for me a t-test result. It says Welsh in here. We'll talk more about the results when we get to a full-on example, but I want to draw your attention to where it has the 95% confidence interval in the t-test results. And we can see that the results in the t-test match very well to the ones that we computed by hand, with a little bit of rounding. Let's talk now about variance assumptions, or in this case, the unequal variance assumption. Now, the variance assumption says that with independent sample t-tests, we should have relatively equal variance. What does that mean? Well, we're dealing with variance in the t-test formulas when we pool our standard estimates. And so what we're hoping is that the variance of group 1 is equal to the variance of group 2, and we can test for this. We can do a separate hypothesis test that says that the two variances are equal, that there is no difference following along with any other null that we're talking about. And the alternative says, well, no, there's some difference. It's not equal to 0, but it's some difference. And actually, let me amend myself. In this case, we're not talking about it being equal to 0. In this case, there's no difference if it's equal to 1. Why 1? Because we can take a ratio of these two variances. Variance of group 1 divided by a variance of the second group, and if they are equal to each other, the same number divided into itself is approximate to 1. And any number off of that is some difference between these two variables here. If you have a higher than 1, then your numerator variance was a larger number than the denominator variance, and if it's smaller than 1, it's flipped, where the denominator was larger than the numerator variance. We can check this equal variance assumption in R, and we do it with a var.test function. var.test, in which case we put in either a vector of data, comma, a vector of second data, so we've got two separate columns specifically, or we can group it with a dependent variable, or y, tilde an x variable that has the grouping. This is going to give you an f statistic, and an f statistic is just a ratio, and it's going to give you a p-value associated with that f statistic. Now keep in mind, this is not the p-value and the results for your original hypothesis testing. This is just to figure out the hypotheses to see if you have equal variance or not. And so you're going to use the same alpha that you use with your t-test, that way you're keeping in line with your analysis, and you're going to fail to reject the null. And if you do so, that means that the variances are relatively equal. If you cannot reject the null, then you have differences in variance. And this test, it's sensitive to sample size. So the larger your sample size, the more likely it is you're going to be statistically significant, even if that ratio is actually close to 1. So pay attention to the ratio number as well as the p-value. Don't rely on just the p-value alone. So when I go ahead and look at this test with the SEI by gender, I would say that the variance of men is equal to the variance of women, and that this difference is going to be equal to 1. So there is no real difference. They are equal. And the alternative says there is a difference between the variances of men and women, and that ratio is not equal to 1. I can plug in my var.test, and I'm using the GSS SEI variable, tilde the sex variable, because I'm doing the grouping version. It generates for me an F test of variances with an F ratio of 0.91769, which is fairly close in rounding terms to 1, a little bit less. And so that says our F value is smaller than 1, so the second group, which in this case is women, had a larger variance than men. We also see that it has a p-value of 0.11. So in this case, we are saying that we're close enough that there's no difference between them. Note, if we're looking at the confidence interval component, the 95% confidence interval could contain the number of 1. So again, iterating that our variances are not equal. Our variances are not different between men and women. And we've satisfied the assumption for the t-test moving forward. If I want, I can also restructure this, so I'm doing the t-test by gender, but instead of doing it with SCI tilde, the sex variable, I can also have it constructed, and I have this example here because your data may be organized differently as well, but I'm doing this, the first version, where I have the SCI variable, and I'm filtering it to only show males, and then I'm doing a comma, not a tilde, but a comma, for the SCI variable, filtered by females. And this is going to create two separate vectors of data that can get compared, and we get the exact same results. Again, focusing that the p-value is 0.1146, and our 95% confidence interval both show us that we're not statistically significant. Just again, to recap here, the assumption for our test is that we have equal variance. The R, when you're working in R, it's going to assume you have unequal variances by default. It's just more commonplace in the real world. And when it does that, it does a variation on the t-test of what it calls the Welsh two-sample t-test. The name Welsh comes from the statistician, and the method of correction that's used inside the t-test, where it changes how it works with the degrees of freedom to help adjust for some of these differences that it's going to see. Now, if you know that you have equal variance and you don't want it to do the Welsh two-sample test, you can put an option inside your t-test called var.equals equals true, and that's going to switch off the Welsh, and it's going to give you the traditional two-sample t-test that we saw before. But keep in mind, t-test is robust against variance when your n gets large. So really, as you get larger and larger, there's going to be almost no difference between the standard student's t and the Welsh approximations. Also keep in mind that when your sample size gets larger, then you can also have differences in variances, which can affect your ability to predict, or, well, not predict, but accidentally have a type 1 error. So keep in mind, my takeaway to you is that Welsh's t-test is also robust to these differences, so just go ahead and use Welsh. If it's similar enough to Z when n gets large, and if it's more conservative by default, so if you're statistically significant with Welsh, you're going to be statistically significant with students, it's just sort of a safer bet to go ahead and use the Welsh. If you want to be more accurate, you can go ahead and use students' t as necessary, but otherwise, Welsh will be just fine. And that wraps up our second video where we're talking about confidence intervals and variance, and I'll see you all next time.